Hey guys, Chili here. Welcome back to Advanced C++ Tutorial 2. Today we're talking about transformations.
Do it!
Now transformations, they lie at the heart of how basically all 2D and 3D graphics are going to be represented on the screen. So what the hell are transformations? Well, movement. Sliding things around on the screen is a transformation. Scaling, making it bigger and smaller, rotation, flipping. 2 out of the next 3 videos are going to be on this topic of transformations, and today's video is going to lay down the foundations for that. Now, in practical terms, one thing that we're going to learn today is we're going to learn how to implement a simple camera object to allow us to pan around in a world and also zoom in and out. Let's get started. Now, what we got right now, we got a simple line. We can draw a single line, but that's boring. That's not going to do for our situation. We want to be able to draw a little scene. So how are we going to do this? Well, we can use our line drawing routine, and we can draw a bunch of connected lines to create a polygon, which is also known as a polyline. And these can form the models for our scene. Now you may be saying, Chili, why don't you just use sprites? They're more interesting. Well, sprites are a lot more complicated to transform. Polylines are very simple. Now we're going to need some data to store our models. And you might be saying, well, what are we going to store? We're going to store lines, right? Because polyline is made up out of lines. But that's not right. Because if you look at the drawLine function, it doesn't take lines, it takes points. It takes 2 points, right? So we want to store our polyline in terms of points. These points here, the points that form the end points of the lines. And we call these points vertices. And get used to hearing that word because you're going to hear it a lot, especially in 3D fundamentals. So the pointy parts of the polygon are the vertices, and we are going to store the vertices, and that will allow us to draw the lines of the polygon. And in 2D, you store vertices, you draw a polyline. In 3D, you store vertices and you draw triangles. Same idea. Alright, so the code to draw a polyline is pretty gosh darn simple. We include vector in graphics.h, and here's our function. It takes a vector of vertices, it takes a color. And all you're going to do is you're going to loop through those vertices and you're going to draw lines from the vertice to the next vertice in the vector. And we're looping not to the last vertice, but to the vertice before the last vertice. And you might be saying, why do we do that? Well, it's quite simple. When I is P1, we draw from P1 to P2. When I is P4, we draw from P4 to P5. When I is P5, we draw from P5 to P6. But P6 doesn't exist, so we would crash. So we only want to loop to here. Now, to do a closed polygon, we also have to draw from P5 to P1. From the last one to the first one, or from the first one to the last one, doesn't matter. And that's handled just outside the loop here. We draw from back to front, and that completes the polyline, making us a closed polygon. And if I just put some test code into compose frame and I run that, you see here we get a nice, beautiful red triangle. All right, now to give ourselves a little more interesting model to work with, I create a little function here, create a class called star with a single static function that returns a vector here. It's going to return a polyline, and it's going to generate it using a little bit of trigonometry. So it's going to generate a star here. And you might be saying, Chili, explain to me how this works because I'm very interested in using trigonometry. And I will say to you, wait until goddamn episode 4, you impatient son of a bitch. So I'll explain how this works in a future episode. But for today, just know that it works. It's going to give us a star. We can specify the number of flares, the points of the star, and the inner and outer radius. So I make a star here, and if I try to draw it, it's going to crash the program. Well, shit. Why the hell is that? Well, pretty much all of your models that you're going to make in 3D, and even our simple 2D polyline models, they're all centered around the origin. They're all centered around 0, 0. And that's for a very good reason to do with rotation. We'll get to that in the future. But just know that you define your models around 0. And what that means is when we try to draw our star as is, parts of it are going to be off the gosh darned screen, and that's no good, right? So what we really want to do is we want an ability to clip our models to the screen so it doesn't try to draw pixels off the screen. And there's a number of ways to do that. There's an algorithm. Where's my window here? There's an algorithm, I think it's called Sutherland-Cohen or something. I don't know. It's a very good algorithm for that. We're not going to use it because it's going to take too long to explain. It's not worth it. So what we're going to use is, let me just make this big. What we're going to do is we're going to do the simplest thing possible, which is quite simply just test to see if X and Y are in the screen. So quite simply, I just perform the conversion to int outside of the put pixel here, and then I test X and Y to see if they're within the screen region, and if so, I draw the pixel. If not, I skip drawing that pixel. So I'm doing per pixel clipping here. It's not the most efficient, but it'll get the job done, and it's not going to make a difference for what we're doing here. And I do the same for when we're looping in the Y. Here I convert the X ahead of time, still do the test, put the pixel. And if we run that, we see we get our star centered at 0, 0, going off the screen. Beautiful. Now we want to move this guy to the center of the screen. So how do we do that? Well, it's pretty simple. To move a model from one place to another here, let's say we want to move it to the right and down by 200, 200. So to do that, all we got to do is move each of its points by 200, 200. And if we move all the points by that amount, then we will have the same model displaced by that amount. Fairly simple concept. So let's put it into practice. So for every frame, we're going to generate a star, and then we are going to add 200, 200 to each vertex on that star, and then we're going to draw it. And if we run that, we should see our star moved a little down and to the right, and here we go. Beautiful star. Love it. All right, now before we go any deeper, there's something I want to address here. Up until now, we've been working with this coordinate system where the origin is in the top left and Y points down. But when we do math bullshits, we often work with a system where the origin is in the middle, Y points up. And it's annoying to have to continually switch between those two systems, to think in one when you're working with math problems, and then to switch to another one when you go into the graphics domain. Wouldn't it be nice if we could just define all of our objects in terms of math coordinates and then draw them like that? Well, we can, with a little bit of an adjustment. So if we want to transform all of our objects so that instead of being drawn at the top left for origin, they were drawn at the middle for origin, what would we have to do? Well, all we'd really need to do was translate them all to the right by half the width of the screen, right? Which is going to be 400. And then we translate them down by half the height, which is 300. And if we did that to all the objects, then all the objects at the center would be drawn at the center of the screen. Not too shabby. Let's give it a shot. Alright, so what I've done here is I've created a class called Coordinate Transformer, and it stores a reference to graphics, and what it does, it has a function called draw close polygon, same signature as the one in graphics. So we can call draw close polygon on the Coordinate Transformer, and it will apply the translation to move an object to the center of the screen, and then it will call draw close polygon on that translated object. So the idea here is now we're creating a little bit of an assembly line or a filter. So instead of passing the model directly to graphics, we now pass it to Coordinate Transformer, which applies some transformation and then passes that result on to graphics. And we could actually chain a bunch of these together, and I'll show that in a little bit. But this idea of this assembly line or this pipeline of processes where we pass our models through, this is super important, and you're going to see this a lot in 3D fundamentals. It forms a lot of the core of how 3D graphics works in hardware and in software. So we create the coordinate transformer in game.h. I add it here. In game.cpp, I initialize it. I give it the reference to graphics, and now we're going to call draw close polygon on the coordinate transformer instead of on graphics, and that will give us our dude. And yeah, it looks like it has been offset because it gets offset here in this loop by 200, 200, and it's offsetting it from the center of the screen now, not from here. So it ends up here. Except, you might be saying, well, Chili, that's not quite right. You said you were going to make it into mathematical coordinate system. But in the mathematical coordinate system, if we were to offset by 200, 200, we wouldn't go in this direction. We would go in this direction, right? 200, 200. So what's the deal? Well, the problem is, of course, y is down. So when we add y, we're going to move down, but we want to move up. So how do we change it? How do we change the direction? We can do an offset. That's easy. But how do we change the goddamn direction? Well, let me give you an idea here. So forget about translation to the center of the screen. Just worry about the direction of the axis for the time being. If we have a point, let me get my red here. If we have a point here in our screen coordinate system, that point relative to the origin in normal coordinates should be around here, right? So if this point were, let's say, negative 50, it would be 50 in normal coordinates. You get what I'm saying here? And if it were negative 100, it would be positive 100 in normal coordinates. So all you've got to do is flip the sign. And how do you flip the sign of something? You multiply by negative 1. So in order to do this flip, all we've got to do is multiply by negative 1. So let's put that into our coordinate transformer. Now it's very important that you get the order correct. You want to do the flip before you do the offset. Can you think of why? We don't want to multiply the entire vertex by negative 1 because that'll also flip the x. That's not a good scene. So what we want to do is we want to do v dot y times and equals negative 1.0f. Yeah, there we go. So why do you think the order is important? Well, think about it. If we flip and then translate, we will get the result of this. But if we translate and flip, well, we translate here, and then we flip, it's going to go way off the goddamn screen, which is not what we want. So you definitely want to flip and then translate first. And this is an important concept in transformations. Some transformations, doesn't matter the order you do them in. Other transformations, it matters a lot the order you do them in. And translation is one of those guys. So around translation, you've got to be careful of the order. And here, around this translation, we want to do the flip first. Good. Now, if we run this, we should get our star in the top right now. And it is indeed in the top right. It's been translated by 200, 200 up here. So now we have our screen translator. And now whatever models we feed into our system, we can feed them in with the screen coordinates. So if we want something at the center of the screen, we just feed it in at a position of 0, 0. And the screen transformer will take care of all the details for us. All right, so up until now, we've been generating a model every frame, doing some translation on it, drawing that guy through the pipeline. But I want to create now a persistent entity that lives in the world and that I can move around freely. So how is this going to look? Well, the entity is going to have a model, std vector vec2, and we'll call that the model, and that is going to store the vertices for the polyline. Now the entity is going to have a constructor that will take its model that it stores. We'll let it take the model by value. That way the caller can choose whether they want to move in resources or copy them. And then here it'll move from that into our member variable. So now we've got our model. We also want to store the position of the entity in the world. So we'll call that vec2 pause, and we'll initially set that equal to 0, 0. Seems good. And now let's add some functions. So we want some functions to, let's say, get the position and set the position. And let's add a function to move the entire model by some displacement. So we'll call this one translate by const vec2 offset, and we'll just add the offset to our position. So now we got some functions to deal with the position of the entity. Now when we draw the entity, we want to get out the model because it is going to be, it's going to need to be drawn. So what we do here is we can go std vector vec2 get polyline, and we can make this entity poop out a polyline, a vector of vec2s, and that will be good. Now when it poops it out, we also want it to apply this transformation of its position to the polyline, and that means it'll be ready for drawing. So what we do, we make a copy of the model vector, and then for each vertex in our poly copy, we just want to do v plus and equals position, and at the end, we want to return poly. So this will poop out a new vec2 that has been translated by the position of our entity, and then we can just draw that. And then in update model, we move the model based on the state of key presses, and in compose frame, we draw the model. And if we run that, it works basically like you'd expect it to. Pressing up goes up, pressing down goes down. All the things work, and it is working, mind you, in mathematical coordinates, not in our dumb graphical coordinates. Now, one thing you might be wondering about is in our entity, we make, every time we draw the model, we make a copy of it. Then we put our transformation on it, our translation, and then we return it by value. It's an R value. It gets moved into the coordinate transformer and gets passed to graphics via constant reference. And you might be saying, well, this copy, why do we have to make this copy every time? Why don't we just work on the model directly every frame? Just move the vertices of the model around, and you could do that, but there is a very good reason why you shouldn't, and that is, well, let's say we've got a simple model. It's just a square, and every frame we perform some transformations on it. We move it around, and there's floating point error. It's very small. You can't tell from frame to frame, but over tens of thousands of frames, the floating point error can add up, and your square can end up being turned into some kind of weird, parallelogram or something. Or maybe it turns into a trapezoid, just based on cumulative errors. But if you start with a fresh model every time, you make a copy of that, and then you do your transformations on the copy, then you don't get this problem. And in reality, if you worked directly on the model every time, some frames you would say, well, I'm not going to move the entity, so I don't even have to change the model at all. I can save myself a lot of extra work. But in reality, in 3D games, the camera is always moving around, objects are always moving around, so there's really not going to be the case where working directly on the model saves you a lot of effort. So in general, you keep your model static, not moving, and you create copies from that and work on the copies. Push the copy down the pipeline, all the transformations on the vertices of the copy, and then throw it away when you're done. All right, now let's take a look at the idea of scaling. Let's say you've got the red square here, and you want to make it twice as big, so you want to scale it up. So what happens to the vertices when you scale from here to here? Well, look at the x and the y coordinates. You can see here that when I scale this up to be twice as large, all we're doing is we're doubling the x and we're doubling the y of each of these vertices. So if you want to scale by some factor, make it twice as large, all you got to do is multiply the vector positions of the vertices by your scaling factor, also known as a scalar. In fact, we call these guys vectors, right? They have multiple components, but numbers with just a single value, we call them scalars. And you use scalars to scale a vector. Funny how that works. Of course, if you multiplied by, say, 0.5, you would scale the object down. It would shrink, right? It's a pretty simple concept. And here's an interesting one. What if you multiplied by, let's say, -1? What would happen? Well, you're just going to negate these guys, you're going to negate these guys, and you're just basically flipping in the X and flipping in the Y. So when we did the coordinate transformer, we were just basically flipping a single axis. But if you scale by negative, you flip both axes. So you can use scaling as a kind of flipping, shrinking, and growing. So in entity.h, let's add some scaling functionality. Float scale is equal to, we start off at 1, the normal scaling, and we might want to, be able to set the scale and get the scale. And we'll leave it at that for now. Now, when it's time to poop out our polyline, we're going to add one extra transformation in here. We're going to go V times and equals scale. This time we're going to do it equally to both components, so we don't have to do v.y or v.x. And remember, you want to scale before you translate. If you do it the opposite way around, you're going to get some weird results. And in game.cpp, in update model, we are going to read mouse events, and we're going to respond to wheel up and wheel down, and we're just going to scale up and down by 5%. So we get the scale, we multiply by 1.05, and we set that. And here, we're just pooping it out. We'll get that scale in there. So let's see if it works. Moving around, mouse down, and we're getting smaller. Mouse up, and we're getting bigger. So now we have scaling and we have translation. All we need is rotation, and we'd be able to do something like, say, make a graphical front end for Box 2D or something like that. But you're going to have to wait a couple of more episodes before we get into rotation. That is going to be, I believe, tutorial 4. The other thing you guys are probably wondering is, well, this is great for, we can scale up our closed polyline models, but what if I want to scale my sprites? How can I do that? And the answer to that is, it's more complicated. You can't just, scale up or down all the pixels, because there's only so many pixels in a sprite. If you scale them up, you're going to get gaps because they're trying to cover a bigger area than their original size. And there are problems with scaling down as well. To do sprites nicely, you really need some more advanced technology, and I will go over that technology. You'll learn that in 3D fundamentals. But if you just use a library like SFML, then you get scaling free out of the box. You just gotta call a function and it'll scale it for you. So you can apply these ideas and just set the scaling value when you draw your sprite, and it'll scale that up and down for you. But keep watching through into 3D fundamentals, and I will teach you the theory behind scaling sprites. And that's going to about do it for part 1. We got our basic transforms down. Now stay tuned for part 2, where we are going to implement a camera component for scrolling in a world scene. We're going to create a more powerful pipeline system. We're going to do some optimizations, and there's going to be some homework with some interesting coding challenges to balance out all that math from the last homework. Until then, thanks for watching. Hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more advanced C++.